I'm happy to be here again today with Haris, and this is episode 5 that we've been working on Haris's theory. And today, Haris is going to help us to understand the theory a little better by summarizing what he's said so far, and then to give some clarifications. And then further, he's going to talk a little bit more about the measurement problem. So I'm really looking forward to this, Haris. I want to apologize to the viewers. It's that time of year when the light coming through my blinds makes this thing on my face when I get too excited and move forward. So I'm going to try to stay back here
Okay.
so I don't get all pockmarked with light. So, Haris, why don't you get started with your summary?
Yes.
And I set it up so you can share screen anytime you need to. And
Great,
I'm
great.
actually going to change the view here so that you're full view so that when you share screen that people will be able to see it better.
Okay, that's perfect.
Yeah.
So, I just wanted to say hi to everyone, and I would like to, as you said in the intro, I would like to summarize a bit all the progress done up to this point, and also share to you with some more insights that I have, and hopefully we are gonna have some times to also show you this construction that I've made, that is inspired by the almost integer construction of Ramanujan. And I will try to replicate that in order to, for all of us to understand better what scientists call the measurement problem. So this is my plan for today. Great. So allow me to share screen. Okay, perfect. Okay, so okay. First of all, I would like to show you a few things about the summary that what I tried to do up to this point, and I would like to focus on this idea of mine that upon pondering on the great discussion that the 3Js had, John Vervaeke, Jonathan Pajot, and also Jordan Peterson, regarding the nomological order and the narrative order. And I tried to show this in the last episode, but now I have it much more clearer in my head, and I can demonstrate it much in a better way. So I was having a discussion with a friend of mine that he's actually involved in what John Vervaeke calls an ecology of practices. From our perspective, we call that ecology of sorts. So that's a different, let's say, naming of it. And these individuals then bring some extra, let's say, feedback to us that we are part of the of research, let's say, or towards us the researchers. So one of the things he told me is that like because he is following and watching our videos, and he told me that I wanted to ask you something. I am sure that you didn't even overthought about how to come up with these constants. And I went to him, yes, you got it. So I just wanted to share that everything came naturally. I didn't even try to bust my head, let's say, in order to come up with this. I just follow the logic that my own theory called T for truth eternal dictates. So when I thought that, okay, how can I calculate, let's say, the Newton's gravitational constant. So as I told you the other time, what I thought was like, since now I am certain that the m value for the speed of light is 5, that actually allows us to make some extra calculations and extra steps, and also some theoretical steps. So the idea there, it was very simple. Like if
So
we
just let me stop you for a second, Haris. Did you mean to have a slide up on the screen? Because all I see is your Google page.
Okay, just give me a quick second. Okay. No, I just wanted to show you this here at this point. Okay, so my understanding is this. When I'm working on the prompt here because it's Google's Chrome prompt. It's nice because it allows us, since it is connected with the internet, it has internet connectivity. It allows us to not only perform some calculations, but also get back the correct unit combo that comes with each different natural constant. So in the case of Newton's gravitational constant, which is something, it's a very small, let's say, number, the correct unit combo is this one right here. So it's the mass to the cube power, and with the kilos and the seconds in this particular order. So in order to be able to for the nomological, let's say, order of things, we need to place that on the denominator. So we could get the actual value that is this one, 6.6743 to the minus 11 with the correct unit combo. And on the denominator now, because as I told you, this is a loss, is a fraction, we can put the calculation that I made in my head. And what is this calculation? Basically, it's the half energy taking as granted as that the M value is 5. That means that the half energy is equal to 2 times M. So that's just 10, which is very helpful in our case, in our human parsing, let's say, case. So we have the half energy to the power of T, and T we had also calculated that as 3 times M, and in this case it's 3 times 5, which is 15. Okay, and what we are doing here, we are multiplying it by, we are placing there the p-value for M equals 5, that is 6 times M plus 1, and that is 31. Okay. I will put a unit here because we are missing one number, just to continue with this presentation. And because this is again is a fraction, I'm gonna divide once again the half energy, but this time in the twice the power of T. So before it was 15, and now it's gonna be 30. Now, so this is the calculation. And just to give you the summary, let's say, of my way of rationale, it was like this. These are all the things I know. The only thing I'm missing, okay, is this Q value. And because I know that my research, let's say, started from having a new interpretation of Einstein's special theory of relativity. And in this interpretation, basically I've linked twin primality with this M value. So in my head, it makes sense that since now I want to address something that has to do with general relativity and therefore with gravity, Newton's gravity, I should not be looking for a twin prime pair that only has distance 2. I should be looking with something that has distance greater than 2. So this 31 is fixed, and we can move on until we can find, let's say, the right Q value. And in this case, the right Q value is not too far away. It's at 2,153. Okay, and now, apologies, here I have to use correctly the parentheses. Now, so in this,
So where did the 2,153 come from?
Okay, 2000, I can explain it to you. It's a bit more technical, but it has a nice story also behind it. So this is what I also explained to my friend, like because he asked me the same thing, how you come up with these things, and I'm sure you have a nice story to explain that. And I got to him, okay, I will share this story with you because it's a nice story. And I practically almost forgot it up to this point that I made this calculation. So when I first started working with as a hobby, as I told you, with prime numbers, at some point I went to the university, so it was back in 2001 when I stopped I finished my military service. So back then I created, let's say, a list of things that I wanted to do, and I noted down, 30, 40 things. And one of them was like I wanted to publish something, even something small, regarding prime numbers. So what I did back then, I came up with a formula that was generating primes, and this formula basically it's let me actually show it to you. Yeah, it has to do with it's this one right here. I submitted it to the Prime Curious page, which is the main page for prime curiosities and prime numbers. And the interesting thing here, this is a page where number aficionados and hobbyists, they supply, let's say, to the editor of the website some trivia regarding some curiosities regarding particular prime numbers. And my formula had to do with 883. Okay, and it was the second, let's say, formula that got submitted under this number. The first one, I'm just reading for those that hear us. The first trivia about this number was something outside of mathematics completely. It had to do with the actress Penelope Cruz and the number that he has tattooed on her right ankle. And actually, it's that number, 883. So that's something small. So I submitted this formula back in 2001. Okay. And this formula has to do with the number, as I told you, 883. And it's a primary generating formula. And what I mean by this, let me just quickly show you. So the formula goes like this. I can write it like in this way. Let's say it's a function. It's a function that takes an input, and this input is something that it's not very small, but it follows these nice generating functions that they can generate a sequence of prime numbers. This is small, it just generates 5. It doesn't generate 41 or 42, but it generates at least 5. So how this formula breaks down, it's very simple. It's like 8 to the power of n plus 8 to the power of n plus 3 to the power of n. This is how it breaks down. And when we go in and instantiate it, as I'm gonna do right now, okay. So we have the first value for n is gonna be 0. The second is gonna be 1, as we are targeting this sequential generation of prime numbers. So let's see how it goes. Now, you see this small formula generates exactly 5 numbers, 5 prime numbers. And it's something very small that, as I told you, it was the very first thing that I did 21 years ago. And in a way, it was nice that I went back to that stage in order to answer to that question about how to complete the calculation for the Newton's gravitational constant. And how I did it is it's very simple, very simple. At least in my head, I was very lucky that I had made this calculation in the past and I remember it. And first of all, I just wanted to tell you that if you remember the dimensions of the monster group, it's 196,883. Okay, so by chance, this formula of mine ends in 883. So it allows me to do some extra calculation that it's nice. And actually what is happening is that what I realize is that when n equals 3, so the number that it generates is this one right here is 1051. What happens in this case is the following. When I multiply this number, times, when I add the number 10 to this number, and I multiply that by 2, the number that I get is this one, which doesn't look very important, but it is in our case. And why it is important? Because this number that we want to tackle, that is 2,153, when you let's say subtract the p-value that we know that is fixed on m equals 5, what you get is the same exact number. So I worked the other way around. So I made this calculation and I said, okay, when I add this number 10 to 1,551 and I multiply it by twice, then I will be able to make this calculation. And just allow me, let me see if I can find it here. One quick second. So, okay. Anyways, apologies for this. I am a bit overwhelmed. Okay, I will do it in another way. Okay. So yeah, this is the way basically that I thought to come up with this number. So I did 2,122 minus 31, sorry, plus 31, and I got the number that I was looking for. And when you multiply 31 times this number, it actually gives you the actual gravitational constant. And the only thing that I am saying at this point is that this is the correct way to do it, because imagine the following thing. First of all, when we say the nomological order, okay, as I told you, it is the constants of nature that they get accompanied with a particular unit combo. Okay. The narrative order does not have, let's say, by default, this unit combo. So taking it a bit further, and we can make the following clarification, let's say. Imagine that on top of not on top, imagine that there is another type of nomological order that is exactly equal to that. Like it has the exact same values, and it also has the exact same unit combo. And how can we imagine this such an indifferent order that is similar to the nomological? One way to name it is to understand it as the cosmological order. So this is not what physicists understand, but maybe that's what cosmologists understand. So these two orders are exactly the same. Now, if we take, and in this, I'm using this as an example. So if we take the understanding of the cosmologist, and we have this exercise where we place on the nominator, let's say, the cosmological order, that is also the narrative order. And if we divide the two orders together, like the cosmological and the narrative, the cosmological and the nomological, because both orders they have this unit combo, the unit combo will cancel out. And since they are equal, it will leave out the sole unit by itself without any unit combo. Now, what I am suggesting is that we can actually make this trick and not only define the nomological order on the denominator divided by the narrative order in order to get the unit with the correct combo, but we can also imagine it that there is another fraction that is equal to this, and it has to do with the cosmological order divided by the narrative order. So somehow this narrative order gets interpolated into these more lawmaking orders of hierarchies of concepts and laws and all of this. And it boils down into what they were discussing, like why is this important and how can we understand this? And my belief is like we can understanding in terms of fractions, in terms of ratios and all of this. So this is what I wanted to add. And please, if you have any questions at this point, you are more than welcome to.
Well, I'm still kind of stuck on 2,153. Why did you decide to add 10 to the 1,051 before you multiplied it times 2?
Okay, this is what
I mean,
I
it
tried.
seems kind of arbitrary. I don't mean any offense, but it sounds
No,
like
no.
you have a particular number in mind you're trying to get, and so you go back and pick up a number and then add something to it and multiply it and subtract in order to get the number that you want that
Yeah,
will fit the formula.
I understand that this is how it can be understood,
Uh-huh.
but believe me, even if that number was a different one, it will not even matter. The actual number, in a way, this calculation it does not depend on that actual number. It's like we're trying to think of how we can re-emulate, let's say, that constant, how we can re-understand it. And this is how I had it in my mind. I don't know if there is any other way for me to put words into it.
No,
Uh,
I think I understand. So you're heading for a particular thing, and this is just kind of the path that you took. And so I don't want to derail your discussion of that, but I did have one other question about the little formula you came up with as a prime generator.
mhm.
That's fascinating.
Thank you.
But why does it only work for five numbers, five powers?
Okay, I can show you another one that it works for more, but it's not for many more. It works for, how do you say? It works for two more, for seven. I actually know two more formulas like that.
These are
Um,
formulas that you came up with?
yeah,
You invented these, yeah. So
yeah, especially
it's
the
it's very
8831.
kind of mysterious.
I can explain that to you how actually other people they are trying to do it like number theories. They are trying to come up with this continuation of prime numbers.
Uh-huh.
It's like an oddity, but it's like it's a puzzle. This is how we think about this. Wait 1 second. Prime generating. Let me just quickly show you the exemplar. Let's say of this 52 primes. Okay, this one it has to do with one of the most famous mathematicians, let's say, Euler, and it's very simple one. As you can see, there are some others here. Mine is not in this high performance region, let's say, but it 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 indeed gives a consecutive number of primes. So you can see all these formulas. They more or less they have the same style, and they have some minute details. You can see that even Legrand came up with something similar. This formula of Euler, it's unbelievable. It generates 40 consecutive primes. So it's n squared plus n plus 41. And it's, let me just do it, n squared plus n plus 41. Okay, so quickly show you a few examples of this. So if I continue, it will go on until number 40, and it will break exactly at 41. And this is why at the very end, Euler placed at 41. So again, we come up with this. Interestingly, now that I notice this, the the symmetry breaking point of Euler's formula, this is nice. I haven't noticed this before. It's our symmetry breaking point of the tape. So that's cool. That's cool. That's cool.
Between 41 and 43, you mean?
Yeah.
Yeah.
You see, it gives from 0 until yeah, actually it starts from 0, so it gives 40, 41. So this is interesting. The last one, it's the square power, let's say, and the next one after that is 41 times 73, which is the n value for m equals 7. So yeah, another formula that I've worked on was I call this one 2 to 3. It's again it's a simple formula. It's 2 times 2 to the. This formula actually is very impressive. I can show you many things that it generates, but maybe we keep that for another time. So yeah. Let me quickly do this. It goes up to 6. Okay, so it generates these numbers here. If you add, if I add the 0, I get another, I get another prime that is 3. So it generates 7. Again, it's not so prolific as the ones coming from Legrand and Euler, but it's good. Also, recently, Teres Tao made some work in these prime generating functions, and they have their own, let's say, character in number theory. So yeah, this is the main things that I was exploring, to be honest, before I started and dealing with the master group and group theory. And of course, they have some very particular interests. I can go on and on. For example, if you analyze this function as a closed system, and you start adding up the numbers and then making taking averages and making this statistical analysis, you can see that it has some it exhibits some nice features like equilibrium and some balancing and all of this. So quite interesting, but it's something, let's say, extra. And in a way, this is what.
So basically, I think what it sounds like what you're saying is that you think maybe the reason that the connection between the primes and the monster group has to do with some information that is kind of buried inside the primes that could tell us more about the basics of the universe. Like equilibrium and things like that. Is
Yes,
that kind of what you're saying? Did I overstate your case?
No, you did not overstate, because I believe, as I told you the other time, I truly believe that the natural language of the prime numbers, it's what I call a proper language, because you can actually, and we will see it in this episode, what we can do with some very, very simple assumptions based on the theory. Like, for example, when you treat it as a formal language and therefore as a formal system, let's say, it allows us to, by virtue of the fundamental theory of arithmetic, we can perform some ideas like coming from computability theory and even Turing with this pumping lemma, and how we can insert, let's say, zeros into our function, in order to extrapolate even more generated prime numbers from it. So this is something that has to do with this theory. And if it's okay, I think I can go.
So yeah, we can go back to your summary where you were working with 2053.
I'm trying to find this. In this format. No. Anyway. Okay, so I've managed to perform this calculation. I tried to approach it from different ways, let's say, as I am doing with most constants that I want to recalculate. Another thing at this point, since we are talking about constants, if you remember during one of the other episodes, what the previous episodes, what I've managed to do is like I tried to once again utilize this information, this piece of information that the m value for the speed of light is fixed on 5, on the number 5. So I use that in order to make an approximation of the dimensionless alpha constant, or the Sommerfeld constant, that is the fine structure constant of the universe. And I was happy with this approximation that I did. It was up to a good fine approximation, but then it came to me that I made another thought that allowed me to perform a different kind of approximation that is even better. It's even a better approximation than the previous one that I had. In the previous time, I tried to tackle the fine structure constant from one way, let's say from the grassroots up, and I achieved that particular result of approximation. This time around, I went from the bottom down. So I did my line of thinking was the opposite. Let's say it was from top down instead of bottom up. And what I thought was the following. I was listening at Bernardo Kastrap talking at one of his frequent podcasts about how he called it. He called it like something like the marriage of 5. And when I heard of that, I thought to myself, if there was any marriage of 5, then it was gonna be with the number 2, because together they make the 10 and the decad and all of this. And then it clicked to me like maybe that's not so crazy of a thought. And it allowed me to do this calculation, like when the value when the value is 2, imagine the p plus q value equals 13 plus 11, that equals to 24. So if we go just one step before this 24 gets complete, like when we go to q plus p minus 1, we will arrive instead of 24 at number 23. So imagine we have this fraction, okay, which is this one here. It's almost close to the unit, but not exactly. And then the only thing we have to do is multiply this by the n value. So p times q, 13 times 11, and that's 143. So when we do this calculation, I arrive at this particular, let's say, approximation for the fine structure constant, 137 point something. It's a bit above the limit that we know. it's the limit is fine structure constant. So the limit actually it's right here 137035999, and what I've calculated is close to this, but not exactly. It has this let's say difference, but it's closer to my previous approximation, so that makes me feel that I am on a good path. And I just wanted to add another thing, some extra piece of information that arises out of this is that, and maybe this I can demonstrate so people they can know how to also do it. Sorry, I can. You see, when we look at this, a number like this, we see the real part that is the integer part, that in this case is the 137. And in the decimal place, we have this number. Okay, so if we take this and we place it into our fraction calculator, and we can say that in this case, there is a trailing digit, the last one that is 6. So we can see that this number is 1/24. So it means that the answer is 137 plus 1 divided by 24, which again is the p plus q value when m equals 2. So this is my line of thinking. I know this is it hasn't been done before, let's say, this particular, let's say, method. So that is why I also want to share my progress in this end. And at this point, I would like to ask you, do you have anything to add here or ask me?
So this is your summary of the fine structure constant.
And my update. Yeah.
Yes. How you came to the fine structure constant from the monster theory, right? But it wasn't only, was there anything else you wanted to summarize from the monster theory? Or was that it? You just wanted to summarize that?
There are a lot of things. I just wanted to clarify that particular thing regarding the, as I told you before the other time, I'm trying to make some progress, let's say, in different fronts. One of these fronts was it had to do with how we can actually start understanding not only in a classical manner this my theory, let's say, how can I can start understanding it not only in a classical manner, but maybe also in a quantum manner. And since I started thinking about this in order to make this summarization of all the progress results, I realized the following thing, that what I understood until now is that, as I told you before, if I can say that the Planck constant, for example, is equal to 4 times n, okay, that means that if I make this reduction that I said the other time, that I am changing the symbol of pi with the natural unit, that means that the reduced Planck constant in my case is equal just to half of that. So in this time is 2 times n. So we have the reduced Planck constant being 2 times n. We have the Planck constant being 4 times n, that is the double. And right in the middle of them, there is 3n. Okay, and this 3n is nice because it's what we've seen in the second episode with the twins from the Oliver Sacks video, that they managed to parse this 37, 37, 37. Okay, that had to do with 3 times a number, let's say. So what I understood is that by focusing on this quantum interpretation of my own theory, I realized that not only the two Planck constants can be redefined for the integers and not for the very small, but also Boltzmann's constant. And Boltzmann constant is equal to 3m. So it goes exactly in the middle between the reduced Planck constant and the the normal constant. So this is a nice result that I've managed to bring forth. And just to make a quick demonstration here, what I mean about the Boltzmann constant is like basically imagine having this. We have this full volume that we can calculate divided by, as I type it is like this, divided by me. It's not it's not so nice to put that, but I can also write it down in this way. So when I make this calculation, for example, when I make 12 times 5 to the, let us assume that m value is equal to 5. So to calculate the volume, the total volume is 12 times 5 squared times the n value, that is 899 in this sense. And on the denominator, we're going to have 4 times m squared. So when we make this calculation, what we get basically is this number here. And this number here is, in fact, the Boltzmann constant for the redefined for the integers, because when you divide it by 3, you will get the n value, as I told you before. So this is a very nice result, and in a different way, what it means? Well, it means that if we take this volume again, and how we can write it down in a different way, I'm working on the prompt now. So to speak with the language of Boltzmann, I have to use logarithms. So the logarithm of W, this is how they call it. I've pinpointed down that this W value, in fact, is equal to 10. Again, we go back to 10. 10 to the power of 4m squared. So it's 10 to the power of 4 times m squared. Sorry. Again, let me put, I did the mistake here. No. Okay. So we can write it down also in this way, like with the logarithm. So this is the natural logarithm for.
Well, hold on a second, Haris. Before you leave this screen where you have the calculator down here,
Yeah.
showing 12 times 5 squared times 899 divided by 4 times 5 squared. I'm not questioning you, but I just want to say that it appears to me that 12 times 5 squared is 300 and 4 times 5 squared is 100. So basically you're saying 3 times 899 over 1 equals 2697, and then you went on to say that if you divided it by 3, you got your 899 back out again, but that's obvious because you multiplied by 3. Then if you divide by 3, you're getting the number back out again.
I know. This is a simple calculation because it's the example that I've used. Because the m value is 5, then it's like how do you say? It rounds up in 10, but it's not difficult because something is simple. It doesn't mean it's not true. You understand? Sometimes you make a calculation and things start to cancel out. That's
Well,
not
then
necessarily a bad thing.
why does 2697 represent the Boltzmann constant?
What I'm saying is that it represents my redefinition of the Boltzmann constant. I try to understand because all these values, they are very small, very, very small. and it's not very easy for someone like me to understand it. So whatever I have to do is I have to, in a way, the project that I am embarking upon during this last month is that I'm trying to make some recalibration of my model in order to be able to accommodate for the quantum world. This is what I'm trying to do.
Okay.
This is what I'm trying to do. So yeah, now the important thing is that this is just a way to define work and W that has to do with this Boltzmann constant. So this is one way that I managed to make this, let's say, small progress. Now, okay, if you want me to show you something else,
Well, I didn't want to derail you. Now you're starting to work on another calculation with log 10.
Mhm.
So what does that calculation reference? The one that you have in the search bar right now.
It's as you see, it's the exact same, but the only thing is that it's the same with the other one, but the one has to do with the logarithm, while the other does not. So one, it includes the logarithm, that is the value of W. So it's TV divided by log W. And this log W, when you pinpoint it down, it goes down to this value right here.
So it comes up again with the same value.
Yeah. The difficult thing is that how can we get a value, let's say, like this one, like so yeah. Now I've just changed it, and you see, I've just increased it into number 7 for the value of 7, and again, once again, it's 3 times the n, of course. So here is 7063 that we've seen before. Okay, so this is something also that I wanted to share with you. Now, if it's okay with you, I can proceed with the measurement problem and this construction that I've made. If it's okay, if you don't want.
Yeah, for sure.
Okay. Great. Okay, so now this goes back to the master basically. Hey, and what we are trying to do is what I'm trying to do here is like I'm trying to create a way to create a construction in order to understand the measurement problem and its implications. So I am using something that I referenced very early on in the very first episode, that is what I call theorem 196,884. And this is theorem M plus 1, where M is the dimensions of the monster, that is 196,883. So here I have a formula that I've denoted as psi with lowercase. And I am using, I'm doing something, I believe it's a bit odd. It's not very frequent that someone, a computer scientist, let's say, stumbles upon the ceiling function. Most of the times we stumble upon the floor function. So this particular construction utilizes the ceiling. And there is a reason why I am doing this, and I will show you. So this construction, first of all, it's the only thing it's doing, it's very similar with the prime generating functions that we've seen before, but this is much more generalized form. It doesn't try to find consecutive primes. It just tries to pinpoint down, like to forge, let's say, the the slice of irreducibility that we understand. There is what you said the other time. There is some a slice, let's say, of reducibility that allows us to claim some things. What I'm trying to do is I'm trying to do exactly this. Like, I'm not saying that. As I told you in the previous episode, I strongly believe in both determinism and free will. Okay, that is the Epicurean or the Eastern Orthodox view. But in my understanding, the way why this is valid, a valid proposition, is because when you take this view, it allows room for indeterminism. So it supposes that it is the free will that give rise to the break of determinism. So in this context, what I'm trying to do is like I'm trying to utilize both what I know to be deterministic and allow room at the same time for the natural randomness of the prime numbers to unfold. This is what I'm trying to do here. So let us consider briefly Ramanujan's almost integer construction. That it's this one right here. It utilizes e to the power of pi squared by a particular number. These numbers, they are not arbitrary. They are very, they have to do with the with number theory. And what Ramanujan came up with in his all those years before, without any calculators and all of this, he came up with this number right here. So he sat down and he said, I want to create an almost integer. So a number that imitates an integer. And in his great genius, he managed to come up with this number that features 12 consecutive nines after the decimal point. So I am trying to emulate this, as in the previous case that I've shown you with that small 883 formula of mine that generates 5 primes. I was trying again to emulate what Euler did with his own 40 prime generating formula. So it's something like this. And I am not I am not targeting to make the exact precision that Ramanujan did. I'm just want to show how exactly we can start doing that, and in a way to start approximating and approaching the ceiling of this value. So the ceiling of this value, of course, as you can see, it ends at 44. Okay, so let's see how we can do. Let's demonstrate. So this is the Ramanujan's calculation. The only thing I'm doing here is that I'm using the language of this calculator in order to be able to perform this calculation with full precision. So in this case, I have to incorporate the square root as a power to the dither, power to the 0.5. So this is the exact same value that Ramanujan constructed. This is the almost integer of Ramanujan. So now, what I am doing is something different. You remember this formula of mine that is 10. So it's like 12 times m squared times n. Now, this has to do with numbers and let's say semi-primes, like numbers that either a prime number or they have a bigger distance. So a number n can have it will break into 2 prime numbers. Now, in the case of the master group and the dimensions of the master group, it breaks down into 3. So it's a different type of number, let's say. And what I am utilizing here is I am doing the following substitution. I am substituting for the value of m squared a probable transcendental number that is pi to the power of pi. Okay, and on the n part, I am replacing it with m plus 1. And now I'm just trying to explain what I'm doing here. I am inserting a meta theorem into my own theory. So I'm taking this theorem, this short theorem that 196,883 plus 1 equals 196,884. And I am doing computations with my own, let's say, theory with this particular modification. Okay, with where I'm using this transcendental number. So if I take this, okay, and I performing at the prompt as I did in a previous episode, you will see that this number is not very round. So when I do multiply by m plus 1, you see what I'm getting here is a nice round number. But on the actual precision calculator, I'm not getting a nice round number. So even if you take your phone and you perform this calculation on your calculator, let's say, you will still get the rounded up version and not this one. Okay, and this for me has to do with the measurement problem. This is the digits we lost in our calculation. There is a rounding up that takes place. In this case, I believe that the calculators, they go a bit crazy because they cannot fully parse a transcendental number as pi to the power of pi. And this is what is happening here. Now, I want to show you something else at this point that, sorry, yes. So it's not only this number that I am saying. I've discovered accidentally, basically, another number that shares this characteristic. And this has to do with the square root of 2 and multiplied by 210. Why these are very important numbers, but not only for my theory, but in general, because this is the dimensions of an A4 sheet of paper. So 210 times the square root of 2, it gives you something like this. And I will show you in a while how we can tackle also this problem. But for now, let me just go back here. So I have this number. As you can see, this is, I started as I want to imitate Ramanujan and I want to construct an almost integer. This is not an almost integer, it's like a magic trick that uses on the calculator. So I'm trying to do something more. So what I'm saying here is like, okay, here I have this number. What happens if I add a fraction? So I come here and I add a very particular fraction that has to do with the inverse of the limit that is 71. So I add this fraction and the value doesn't change. Understand? This is, so what does it mean? It means that there is room. Imagine this as a jar, okay, a mason jar, let's say, where you have a lot of small rocks inside. And then there is still space inside it. So when you add some sand, it will still fill in, right? So this is what we are trying to do. Now, in this case here, sorry, yes, this is the case that we are now. So as you can see, just by adding that limit, the inverse of the limit, we went from 0.985, we went up to this nice 999 approximation, okay? But what I say is like, no, I want to pour more sand into it to see if it still works when the symmetry will break, let's say, in this thing. And so I come up here and I say, okay, I'm going to add another fraction. And these fractions that I add, they are, again, they are not random, but again, I am adding this fraction that is the inverse of another number that also has to do with the prime, with the master group, with the higher, let's say, manifestation of the master group. And in this way, I am still at only 3 nines. So I want to push a bit more. And how do we push a bit more? Basically, what this third fraction that still doesn't give us what I am targeting for was 4 nines, okay, for the purposes of this demonstration. So when I add the same fraction again, I get these 4 nines. So I'm getting even closer to the ceiling. Once again, I am not approximated as good, let's say, as Ramanujan did with the 12 consecutive nines after the decimal point, but this is good enough because it's like 1/3 of that approximation. It's 4. So now, as you can see, by yeah. So I've added all these numbers and still there is room. So what will happen if I add, you might ask, another one? So it goes above the ceiling. So just by adding another one, so in a way, this is the limited case for this. So let me show this again. It goes above the ceiling, and above the ceiling is something that we don't have any interest into it, let's say. It will be erroneous to move beyond the ceiling. Now we'll explain to you why it will be erroneous and why we want to focus exactly on the ceiling, not approximating the ceiling always, because this is what I understand science is doing. And this is the measurement problem from my perspective. We constantly try to approach a limit. Let's say if we're targeting, let's say, a value between 0 and 1, we stumble like on 0.999999, and we never go to the actual integer value that is the actual limit. So this is the construction that I have done. And just to move quickly to the other example with the A4 and the square root of 2, I can utilize, because I told you whatever knowledge I gain from every little trick I am doing and it's working, I'm trying to see if it has this spillover effect into other areas or other calculations or whatever. So I've done exactly the same thing for this case, and I've noticed that I went up to 3, as I've done in the case with the master, but it allowed me to move a bit more in this case. So when I go to the 6, I once again go above the ceiling. So in this case of the square root of 2, this is the approximation, let's say, that is safe in a way. So now, do you want to ask me something at this stage, or do you want me to proceed with why this is important?
Oh, I think you should proceed with why it's important. Yeah,
Okay.
we only have about 15 minutes left, so I want you to be able to get to your main point.
Okay, so let me go back here. Now, okay. So now I have to shift the focus here. Here I just written down some ways in order to calculate this the dimensions of the master in a nice way, in a formulaic way. The first one has to do with 12 times this M value that I've calculated, that is 231, plus 1 times the limit, that is Q. And another formulation has to do with the penultimate prime number that belongs to the prime, that is 59. And this is a nice approximation. This is a nice formulation of for the dimensions of the master, because it allows us to have a 3D visualization of these dimensions. It's like this here. I ran this by Wolfram Alpha. So this is the let's say the input formulation, and this is the 3D plot. And as I see this, I believe that in a way it what do you say? It's again an instantiation of the measurement problem, because in a way, as I can see this graph is cutting down because it is inside a box. If the box was bigger, this plot will unfold even more on the outside. But this is something different. This has to do with visualization, let's say. So another formulation for the exact same has to do with this value here. I will not get into details. What I will do is I will show you why this is important. Now, when we calculate this psi value, in a way, what I'm saying is that the number that you are gonna get when you apply the ceiling function onto this, 12 times pi to the pi times 196,884, you will get a new prime that is higher than the limit, that is 71, times 10. And this is why I write it 2 times 5 and 2 to the a power times 5 to the b power, because it's important to note that a equals b equals 1. So why this is important? When I go and take this value of psi, and I just add 1, what I get back this number 71, that is my limit, that is of prime interest for me. I'm getting this prime number that I've used in my construction that I've showed you with the fractions. And I'm also getting 361. So what I'm saying, what I notice here is the following. Okay, I make this calculation. I'm getting one prime number that is larger than 71. It's a large prime, let's say. But I'm also getting this semi-prime that I don't really want. So can I come up with a different formulation or an extension of this psi formula in order to generate more prime numbers and understand how more prime numbers can be generated? And actually, we can define these two extensions of psi according to Spinoza's extension principle. So I'm going back to the philosophy, let's say. And I call this psi plus and psi star. Now, I define this in the following way. Psi plus equals the value that psi has, that we've seen is that integer, 86 something. And what I add here, I am using the exact same reformulation as before. And I'm just building upon the feedback that I had from before. So I know that I've utilized this 71, and I'm also utilizing this. I am noticing that I have this 10 multiplier on the right-hand side. So the idea is to bring this on the left-hand side and see what happens. And in fact, what is happening is that when I do this thing with all the same conditions that apply, what I'm getting back is this number right here. That is an even larger prime. That is psi star plus. And when I just add 1, what I'm seeing here is the following. I've made some progress from the previous case, because the previous case, it included a semi-prime, that is 361, that is 19 times 19. And in this case, I have a number that is actually in the same format as the master dimensions. So it's 3 different prime numbers. Now, once again, I have this 71, which is appropriate. And we can proceed to the last extension in this way. And here comes the pumping lemma for formal language that says that we can insert some carefully selected terms that are associated with psi and then J invariant in order to construct this psi star. And this psi star, basically, once again, it builds on this same principle of multiplying. So we're taking the number of psi that we calculated. We have this multiplication by the limit and by 10. And we add this. Honestly, it's very carefully selected terms. Like you cannot remove any of this. And these are not arbitrary. They are coming from the J invariant. So when we come here and finally do this extension as well, as you see, these prime numbers get bigger and bigger. So, okay, finally, what we are getting, once again, the value for psi star, it's a multiplicate of 10. It's a prime times 10. And when we add just 1, what we get is, this time we get 71, which is the limit. We get the extended limit, that is also a prime, that is 3,361. And we get a nice big prime over here. So what does this mean? This means that I can take this latest formulation, and when I divide it by my 2 limits, that is 71 and 361, I'm gonna get a nice prime number. Now, what I meant before is working is because here, and I start adding some.
Haris, I seem to have lost your feed, Haris, but I'm going to add this question in here. It looks to me that what you did was multiply by 71 times 3361 times the big prime number, and then you divided by 71 times 3361, and you got the prime number back out again. But if you multiply by it and then divide by it, you're always going to get the same number back out, aren't you?
No, it's not the same number. This is a big number. That this is the value, let's say, that is psi star plus 1, give us this big number. Okay. Now, what I'm saying is that by doing this, by considering that these 2 values of the limit here, they are fixed, we can claim that we can fix them. So we can say that psi star plus 1 divided by these 2 limits, they will give rise to 1 prime number. And in this case, the prime number is, of course, this. But when I go and, for example, in the formulation of psi plus, I go and I start adding zeros, I will keep getting more prime numbers. I will not get all the way continuous prime numbers, but I will discover many prime numbers with this case. And from my perspective, this has to do with with what Riemann was saying about the non-trivial zeros that exist, let's say.
So you found a new prime number generator.
I think yes. I think yes. And I can show. No, let me see how I can quickly do this. Okay. Okay. Ah,
So
okay.
this will have to be the last. What you're showing me right now will have to be the last thing because then my time
Yeah.
is up. So
Okay. No worries. Just trying to find. Okay. This is just one example, a very short one. Okay, so this is what I mean. In this case, we've discovered a prime number with 19 digits in the let's say the terminal case, and when we added some extra zeros, we've discovered a prime number that is 36 digits. So we can continue doing this, and in this way, it's a generating function. And the whole trick is that we just divided, let's say, these numbers.
so that's why you call them non-trivial zeros.
Yeah, yeah. Apologies if I'm not able to do it in a more clarifying manner, but okay. So
Well, I apologize for having had so many questions because I know that took up a lot of your time trying to explain
no,
my
no, no,
question.
no, no, don't worry. I will stop sharing in order to come back to it. Okay, great.
Yeah.
Um,
So my brain is kind of tired.
apologies,
No,
apologies.
no, it's just because my brain is limited when it comes to looking at all these mathematical things. But one of these days, I would like to just have a talk with you about this idea of the nomological and the narrative, but
Mhm.
not
Yes.
necessarily from a mathematical standpoint, right?
Philosophy. Yeah.
Philosophical standpoint, because I think that would even help me understand what you're doing mathematically if I understood the philosophy behind it a little bit better. So, thank you for joining me again, Haris, and I look forward to the next time. And I hope we get some good comments. Another good comment just came up today on, I think it was episode 1. So you might want to look back at some of the older episodes because some new comments are coming in that are quite interesting.
Oh, that's great. That's great.
Yeah,
That's
yeah. And for those who are still listening, I just want to mention that I have an episode coming up soon with Wolfgang Smith and Jonathan Pajot. So I'm excited about that and look forward to being with everybody again.
yeah. Karen, just
Uh-huh.
before close, a very small final, let's say, thing. This has to do, this is a table with the isotope half-lives, okay? And what
Isotope of what? Oh, half-life.
isotope half-lives, yes.
Uh-huh.
And this is a standard table of what is stable and what is unstable. And it has these the scales, let's say, in seconds and microseconds and years. And what I just wanted to tell you is that this line that what it says here, Z equals N, it means that these half-lives, they follow this diagonal line, okay? So up to a specific point, they indeed follow this diagonal line, but at some point they just stop. And I did what we said the other time. I zoomed in and I calculated that, and I figured out that the exact point where they skew, it's at 54.5 seconds, let's say. So this is something also that I would like to share with you. This is something completely different, but it has to do with all the work that I'm doing. Because when you calculate, for example, m value equals 5, you can actually go there and you can see that up to that point before it goes up, everything falls exactly on the line. So my prime calculating method allows me to go directly to that line and see what's there. This is the other thing I wanted to show to you and to your
Yeah, that
audience.
would be very interesting. Okay, well, we've got something to
Great,
look at next time then. Thank you,
great,
Haris.
great.
Have,
Thank you. Bye.
yeah, have a great
Bye.
day.
Bye. You too. You too. Bye. It's a pleasure.